Hello, my students. Now this will begin a brief discussion of how we can use electronegativity differences to diagnose if we are dealing with a covalent, ionic, or metallic bond. Just to review briefly, usually we can diagnose the type of bond based upon element composition. If we have metals bonded with other metals, it's metallic bonding. Metals bound with nonmetals, it's ionic. Nonmetals bound with other nonmetals, it would be covalent. So notice we are excluding that noble gases. We are just looking at true electronegativities, not when elements are forced to react, so we're just assuming that noble gases carry the electronegativity values of 0. Now, if we look at the bonding between sodium and chlorine, we know that delivers an ionic bond where there's a transfer of electrons. The cation and anion cling together because of electrostatic attraction. However, to prove that, chlorine has an electronegativity value of 3. Sodium has an electronegativity value of 0.96. And if we subtract that, if we find the difference between them, and let's see, 10, 9, 0, 2, 2.04, that delivers what would fall in the realm of an ionic bond. The relative scale is shown, and your book goes through this also. If we have an electronegativity difference between our elements of 0 to 0.3, it falls under the classification of nonpolar covalent. 0.3 and 1.7 polar covalent, 1.7 and 3.3 ionic. So our sodium and chlorine difference, 2.04, puts us in the ionic realm, which we know that. But what is the business with this polar and nonpolar covalent? If we go back to the basic differences between our different types of bonds, and back to the Sesame Street version of sharing electrons in covalent bonding, well, it's never quite as friendly as we would like it to be. Truly, the only true fair sharing where elements truly are equally sharing the electrons would be when we have one element bound to itself. Then they have equal strengths at pulling the electrons in the bond. Like in the case of fluorine and fluorine, electronegativity of 4 and 4, nobody wins the electrons. However, what if it's between fluorine and chlorine? Fluorine has a value of 4, chlorine a value of 3. He is much stronger at pulling electrons, and we know why, because he's the smaller element compared to chlorine. So when they share electrons, the electrons are going to spend so much more time around fluorine. So if we would try to, just show that graphically, the electrons, which here are being shared equally, here are spending so much more time around fluorine, much less time around chlorine. So much more time around fluorine, much less around chlorine. Now, in ionic bonding, the metal gets the full positive charge because it's lost an electron. The nonmetal gets the full negative charge because it is taken and is keeping the electron. And they're fine with that. There's no sharing. The electrostatic attraction accomplishes the bonding. Here, there is a sharing. They need each other, but it's not an equal sharing. Where there's an unequal sharing, which is the majority of covalent bonds, it is called a polar covalent bond. Where there's equal sharing, that is a nonpolar covalent bond. So, of our covalent bond, there's actually 2 more branches where you would be polar versus nonpolar. Now, as far as electronegativity differences go, if our elements have a difference in electronegativity of 0.0 up to 0.3, then it's nonpolar. If it is 0.3 up to 1.7, then it would be polar covalent. If it is 1.7 or above, we put it in the ionic realm. So remember, the sodium and chlorine fell here. The case of chlorine and fluorine being a difference of 1 would fall in the polar covalent. Let's look at another. How about carbon and hydrogen? Okay, carbon is 2.56. Hydrogen is 2.20. So a difference of 0.36. That would make it polar covalent. Basically, elements need to be right next to each other on the periodic table to deliver a fairly equal sharing in the case of being covalent. Now, it could be, however, like in the case of HF. Now, again, fluorine has a value of 4, hydrogen, that value of 2.20. Subtracting these, we get 1.80, which puts us in what would be classified as ionic. Okay, now that's where composition will trump electronegativity difference. In the case of HF, they're nonmetals. They're going to be sharing electrons. Now, it is going to be so unequal that it's almost classified as ionic. However, composition trumps it, so it's still polar covalent. It's just very, very polar covalent. And if we look at this graphic, as we differ in our electronegativity differences, we get more and more unequal in our sharing, or more and more close to being like ionic, a transfer of electrons. So as our electronegativity differences increase, what we call the percent of ionic character, we get much, much, much closer to resembling a complete transfer of electrons, unequal sharing. Where when our electronegativity difference creeps closer to 0, we increase the covalent character. I think this is another good graphic. As the electronegativity difference increases, so does the ionic character. As the electronegativity difference decreases, so does the covalent character, or increases the covalent character. And this is just a graphic. It's showing, electrons and where they're spending their time. Now, this would be our cation and anion. The anion keeps the electron. The cation has lost, full positive, a full negative. In a polar covalent, where the electrons are spending more of their time, that is going to be a more negative part of our bond. It gets assigned this partial negative. It looks like a kind of a strange music note. You can see the negative on either side, but this side is going to get the partial negative charge, and this side is partial positive. It's not a full giving up and taking. It's just kind of negative and kind of positive. Where if we have a sharing, no one wins. So there's one side that's more negative or more positive than the other. So whichever is the more electronegative element, that's where the electrons are going to be spending more of their time. So if we go back to the case of HF, the electrons are going to be spending more of their time around the more electronegative. That would get the negative assignment, and by default, the electrons are going to spend less time with hydrogen. That gets the partial positive. Best of luck. Try the questions that I've asked you to do for homework, and this gets us started on classifying bonding by electronegativity difference.